The pigeonhole principle. The pigeonhole principle states that if n pigeons fly into m pigeonholes and n is larger than m, then at least one hole must contain 2 or more pigeons. Illustrated in this figure here. This is one of those examples of mathematically formalizing common sense. If you have more pigeons than holes, then one pigeonhole must have at least one extra pigeon in it. Let's see here. Figure A shows pigeons perched next to their holes, and B shows the correspondence from pigeons to pigeonholes. The pigeonhole concept is sometimes called this guy's name, which I don't know how to pronounce, because it was first stated formally by him in the 1800s. So the pigeonhole principle, a function from one finite set to a smaller finite set cannot be one-to-one. There must be at least 2 elements in the domain that have the same image in the codomain. So, examples. In a group of 6 people, must there be at least 2 who were born in the same month? In a group of 13 people, must there be at least 2 people who were born in the same month? No? If 6 people could all be born in different months, so no. But a group of 13, there's only 12 months, so one person must have the same month as somebody else. Among the residents of New York City, must there be at least 2 people with the same number of hairs on their heads? Well, that's we already went through the 6 people and 13 people in the same month. And you can see here by looking at the diagrams that 13 people have one must have the same birth month as at least one other person. So B, the answer is yes. In this example, the pigeons are the people of New York City, and the pigeonholes are all the possible numbers of hairs on any individual's head. It is known that the population of New York City is at least 8 million people. Also, the maximum number of hairs on any person's head is known to be less than 300,000. Define a function of h from the set of people of New York to the set of number of hairs on one's head, and you'll see that there are more people in New York than there are hairs on the people's heads by a factor of a couple of dozen. Since the number of people in New York City is larger than the number of possible hairs on their heads, the function h is not one-to-one. At least 2 arrows point to the same number. And this means that at least 2 people have the same number of hairs on their heads. Application to decimal expansions of fractions. Well, one important consequence of the pigeonhole principle is the fact that the decimal expansion of any rational number either terminates or repeats. A terminating decimal is one like 3.625, and repeating decimal is like this here, where the bar over the digits 246 indicate that these digits are repeated forever. So let a and b be integers and consider a fraction a over b. where for simplicity A and B are both assumed to be positive. The decimal expansion of A over B is obtained by dividing A by B, as illustrated here for A equals 3 and B equals 14. So, let R0 be A, let R1, R2, R3, etc. be the successive remainders obtained in the long division of A divided by B. By the quotient remainder theorem, each remainder must be between 0 and B minus 1. If some remainder R equals 0, Ri equals 0, then the division terminates, and A over B has a terminating decimal expansion. If no R sub I equals 0, then the division process and hence the sequence of remainders continues forever. By the pigeonhole principle, since there are more remainders than values that the remainders can take, some remainder value must repeat. R sub j equals R sub k for some indices j and k, with j being less than k. This is illustrated below for A equals 3 and B equals 14. R1 and R7 both equal 2. It follows that the decimal digits obtained from the divisions between R sub j and R sub k minus 1 repeat forever. In the case of 3 divided by 14, the repetition begins with R equals R7 equals 2, and which equals R sub I, and the decimal expansion repeats the quotients obtained from the divisions from R1 through R6 forever. Generalized pigeonhole principle. A generalization of the pigeonhole principle states that if n pigeons fly into m pigeonholes, and for some positive integer k times m is and k times m is less than n, then at least one pigeonhole contains k plus 1 or more pigeons. This is illustrated in figure 942. M equals 4, n equals 9, and k equals 2. Since 2 times 4 is less than 9, at least one pigeonhole contains 3, 2 plus 1, or more pigeons. In this example, it's pigeonhole 3. So the generalized pigeonhole principle is for any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if k times m is less than n, then there is some y that's an element of big Y, such that little y is the image of at least k plus 1 distinct elements of x. Now show how the generalized pigeonhole principle implies that in a group of 85 people, at least 4 must have the same last initial. There's 26 letters in the alphabet. 3 times 26 is 78. So that means that there would be, 7 left over. So 7 must have, 7 would have to go into letters making at least 4 must have the same last initial at some point. In this example, the pigeons are the 85 people and the pigeonholes are the 26 possible last initials of their names. Consider the function L from people to initials defined by the following arrow diagram. Now, you can see that there are more pigeons than pigeonholes, so you're going to have some overlap. Since 3 times 26 is less than 85, the generalized pigeonhole principle states that some initial must be the image of at least 3 plus 1 people. Thus, at least 4 people have the same last initial. Consider the following contrapositive form of the generalized pigeonhole principle. For any function f from a finite set x with n elements to a finite set y with m elements, and for any positive integer k, if for each a little y being an element of big Y, the inverse function of y has at most k elements. Then x has at most k times m elements. In other words, n is less than or equal to k times m. All right, that's the contrapositive form of the pigeonhole principle. Now, proof of the pigeonhole principle. The truth of the pigeonhole principle depends essentially on that the sets are involved of being finite. We know that a set is called finite if and only if it is the empty set or there is a one-to-one correspondence from 1 to n to it, where n is a positive integer. In the first case, the number of elements in the set is said to be 0. In the second case, it is then said to be n. A set that is not finite is called infinite. Just stating what we already know there. Thus, any finite set is either empty or can be written in the form of x sub 1, x sub 2, etc. to x sub n, where n is a positive integer. So, restating the pigeonhole principle, for any function f from a finite set x with n elements to a finite set y with m elements, if n is greater than m, then f is not one-to-one. An important theorem that follows from the pigeonhole principle states that a function from one finite set to another finite set of the same size is one-to-one if and only if it is onto. This result does not hold for infinite sets. So, one-to-one and onto for finite sets. Let x and y be finite sets with the same number of elements, and suppose that f is a function from x to y, then f is one-to-one if and only if f is onto. And that's it for that one. Let's see if this behaves. Yeah. All right. Apparently not. Counting and probability continued with counting subsets of a set. Combinations. Well, the number of subsets of a size R that can be chosen from S equals the number of subsets of size R that S has. Each individual subset of size R is called an R combination of the set. Definition. R combination. Let n and R be non-negative integers with R being less than or equal to n. An R combination of a set of n elements is a subset of R of the n elements. The notation here reads n choose R denotes the number of subsets of size R, or R combinations, that can be formed from a set of n elements. Consider a set of 4 people, Ann, Bob, Sid, and Dan. Given the set, each subset of size 3 is a 3 combination of its elements. List all the 3 combinations of the set. Use the result of part A to find 4 choose 3. In how many ways can the people in the set form a committee of size 3? Well, that would be the 4 choose 3 from B. But the number of each set that can be each subset of size 3 that can be obtained by leaving out one of the elements of the set is represented here. So there are 4 items in the list of 3 combinations. So 4 choose 3 equals 4. The number of ways for people to be to form a committee of size 3 is the number of distinct committees, which is the same as the number of subsets of size 3. So there is 4 ways people can be set in the set can form a committee of size 3. There are 2 distinct methods that can be used to select R from objects from a set of n elements. In an ordered selection, it is not only what elements are chosen, but also the order in which they are chosen that matters. 2 ordered selections are said to be the same if the elements chosen are the same, and also if the elements are chosen in the same order. An ordered selection of R elements from a set of n elements is an R permutation of the set. In an unordered selection, on the other hand, it is only the identity of the chosen elements that matters. 2 unordered selections are said to be the same if they consist of the same elements, regardless of the order in which the elements are chosen. An unordered selection of R elements from a set of n elements is the same as a subset of size R, or an R combination of the set. How many unordered selections of 2 elements can be made from the set 0, 1, 2, and 3? Now, an unordered selection of 2 elements from the set is the same as a 2 combination, or a subset of size 2, taken from the set. This is listed systematically here. Since the listing exhausts all possibilities, there are 6 subsets in all. Thus, 4 choose 2 equals 6, which is the unordered number of selections of 2 elements from a set of 4. When the values of n and R are small, it is reasonable to calculate the values of n choose R using the method of complete enumeration. But when n and R are large, it is not feasible to compute these numbers by listing and counting all possibilities. The general values of n choose R can be found by a somewhat indirect but simple method. An equation is derived that contains n choose R as a factor. Then this equation is solved to obtain a formula for n choose R. Write all two permutations of the set 1, 2, 3, 0, 1, 2, and 3. Find an equation relating the number of two permutations and the number of two combinations for choose 2, and solve this equation for 4 choose 2. Well, according to 923, the number of two permutations of the set is P of 4 and 2, which equals 4 factorial over 4 minus 2 quantity factorial, which equals 12. So theorem 923 states that if n and r are integers and 1 is less than or equal to r, which is less than or equal to n, then the number of r permutations of the set of n elements is given by this formula here, or equivalently, n factorial over n minus r factorial. Now, the act of constructing a two permutation of the set can be thought of as a two-step process. Choose a subset of two elements from the set, and then step 2, choose an ordering for the two-element subset. This process is illustrated by this possibility tree, and it you can see the relationship between permutations and combinations. The combinations, there's only 6, but for each combination, there's 2 permutations for it. So a total of 12 permutations. The number of ways to perform step 1 is 4 choose 2, the same as the number of subsets of size 2 that can be chosen from the set. Number of ways to perform step 2 is 2 factorial. The number of ways to order the elements in a subset of size 2. Because the number of ways of performing the whole process is the number of 2 permutations of the set, which equals P of 4 and 2, it follows that from the product rule that P of 4 and 2 is equal to 4 choose 2 times 2 factorial. Solving for 4 choose 2 gives 4 choose 2 equals P of 4 and 2 over 2 factorial. We know that P of 4 and 2 equals 4 factorial over 4 minus 2 factorial. So substituting yields 4 factorial over 2 factorial times 4 minus 2 quantity factorial. The number of subsets of size r, therefore, or r combinations can be chosen from a set of n elements, is given by the formula n factorial over r factorial times n minus r quantity factorial, where n and r are non-negative number integers with r less than or equal to n. Consider again the problem of choosing 5 members from a group of 12 to work as a team on a special project. How many distinct 5-person teams can be chosen? Now, the number of distinct 5-person teams is the same as the set subsets of size 5 that can be chosen from a set of 12. This number is 12 choose 5. By theorem 951, that is equal to 12 factorial over 5 factorial times 12 minus 5 quantity factorial. which when you do a lot of canceling out, yields 11 times 9 times 8, which is 792. So there are 792 distinct 5-person teams. Now use the multiplication rule to show that K sub M and N, a complete bipartite graph on M and N vertices, has M times N edges. And use two combinations to show that K sub N, a complete graph on N vertices, has N times N minus 1 over 2 edges. A complete bipartite graph is a simple graph whose vertices can be divided into two distinct non-overlapping sets, say V and M, or V and W, in such a way that there's exactly one edge from each vertex of V to each vertex of W, and no other vertexes in the graph. Think of constructing the edges between vertices of V and W as an m-step process. For each integer k from 1 through m, draw exactly one edge from V sub k to each of the n vertices of W. Because each step can be performed in n ways and there are m steps, by the multiplication rule, there are m times n ways to construct all the edges. Therefore, k sub m and n has m times n edges. Now, a complete graph on k sub n, a complete graph on n vertices is a simple graph with n vertices and exactly one edge between each pair of vertices. If n equals 1, then k has one vertex and no edges. And since n times n minus 1 over 2 equals 0, then k sub n has n times n minus 1 over 2 edges. If n is greater than or equal to 2, then, since any two distinct vertices of k sub n are connected by exactly one edge, there are as many edges in k sub n as there are subsets of the size 2 in the set of n vertices. By theorem 951, there are n choose 2 such sets, and n choose 2 equals n factorial over 2 factorial times n minus 2 factorial. When you multiply that out and do a bunch of canceling and all that sort of stuff, you get n times n minus 1 over 2. Hence, k sub n has n times n minus 1 edges. Now, the game of poker is played with an ordinary deck of 52 cards. Various 5-card holdings are given special names, and certain holdings beat certain other holdings. The named holdings are listed from highest to lowest below. Need to go through all the different hands of poker? You want to go through them? Do we need to go through them? Because they go through in detail and formally explain what each one is. One pair, or no pairs, one pair, two pair, three of a kind, straight, flush, full house, four of a kind, straight flush, royal flush. In that order, in ascending order, that's the way they go. But how many 5-card poker hands contain 2 pairs? Well, and then what's the probability that a hand contains 2 pairs? Well, consider forming a hand with 2 pairs as a 4-step process. Choose 2 denominations for the pairs. Choose 2 cards from the smaller denomination. Choose 2 cards from the larger denomination. And then choose 1 card from those remaining. The number of ways to perform step 1 is 13. Choose 2 because there are 13 denominations in all. The number of ways of performing steps 2 and 3 is 4. Choose 2 because there are 4 cards of each denomination, 1 of each suit. The number of ways to perform step 4 is 44. Choose 1 because the 5th card is chosen from the 11 denominations not included in the pair, and there are 4 cards of each denomination. So the total number of hands with 2 pairs is 13. Choose 2 times 4. Choose 2 times 4. Choose 2 times 44. Choose 1. Multiply it out, do a bunch of canceling, all that sort of stuff, and you get 78 times 6 times 6 times 44, or 123,552. And the probability of getting such a hand, the total number of 5-card hands from an ordinary deck of cards is almost 2.6 million. Thus, if the hands are equally likely, the probability of obtaining a hand with 2 cards, or 2 pairs, is approximately 4.75%. So, makes getting a royal flush look really difficult because there's only 4 combinations out of 2.6 million. So, I've actually gotten a royal flush in playing in Vegas. So, I beat the odds. It is possible. But anyway, consider the various ways of ordering the letters in the word Mississippi. Here are some examples. How many distinguishable orderings are there? Don't remember if you're right or not, but imagine placing the 11 letters of Mississippi in one after another into 11 positions. Because the copies of the same letter cannot be distinguished from one another, once the positions for a certain letter are known, then all copies of the letter can go into the positions in any order. So there is a 4-step process here. Choose a subset of 4 positions for the S's, a subset of 4 positions for the I's, a subset of 2 positions for the P's, and a subset for the 1 position for the M. So, since there's 11 positions in all, there are 11 choose 4 subsets of 4 positions for the S's. Since the 4 S's are in place, there are 7 positions that remain empty. So there are 7 choose 4 subsets of 4 positions for the I's. After the I's are in place, there are 3 positions left empty, so there are 3 choose 2 subsets of the 2 positions for the P's. That leaves just 1 position for the M, but 1, so that's 1. So by the multiplication rule, it's 11 choose 4 times 7 choose 4 times 3 choose 2 times 1. Multiply it out, do a bunch of cancellation, and you get 34,000 8,650. So permutations with sets of indistinguishable objects. Theorem 952. Suppose a collection consists of n objects, of which n are of type 1, n1 are of type 1, and n sub 2 are of type 2, etc., to n sub k. And suppose that n plus 1 plus n plus 2, n sub 2 plus etc. to n sub k equals n. Then the number of distinguishable permutations of the n objects is n factorial over n1 factorial times n2 factorial times n3 factorial, etc., to n times n sub k factorial. Some advice about counting. Now, I don't really like this example that they give here. A group consists of 5 men and 7 women. How many teams of 5 contain at least 1 man? Imagine constructing a team as a 2-step process. Choose a subset of 1 man. This is the incorrect way of doing things. Choose a subset of 1 man from the 5 men. Choose a subset of 4 others from the remaining 11 people. Hence, by the multiplication rule, there are 5 choose 1 times 11 choose 4, or 1650 5-person teams that consist of at least 1 man. But the problem with the solution above is that some teams are counted more than once. Suppose the men are these 5 guys, and the women are these 7, or what is it? Yeah, 7 ladies. According to the method described previously, one possible outcome of the 2-step process is given here. And in the case of the team, another possible outcome is this, with just the outcome of step 2 being, a different step 1 and the same, but overall the same names in the group, which gives the team 2 different branches of the possibility tree, so it is counted twice. They tell you why it's wrong, but they don't tell you how to do it. The slides don't tell you how to do it right, which is kind of frustrating. But anyway, that's it for that slide deck. And on to section 6. Let's see if it... Are combinations with repetition allowed? Well, how many ways are there to choose R elements without regard to order from a set of n elements if repetition is allowed? A good way to imagine this is to visualize n elements as categories of objects from which multiple selections can be made. Definition and notation. An R combination with repetition allowed, or a multiset of size R, chosen from a set X of n elements, is an unordered selection of elements taken from X with repetition allowed. If X equals X sub 1, X sub 2, etc. to X sub n, we write that an R combination with repetition allowed, or multiset of size R, as X sub I sub 1, X sub I sub 2, etc. to X sub I sub j. where each x sub I sub j is in X, and some of the x sub I sub j may equal each other. Write a complete list to find the number of 3 combinations with repetition allowed, or multi-sets of 3 that can be selected from the set 1, 2, 3, and 4. Observe that because the order in which the elements are chosen does not matter, the elements of each selection may be written in increasing order, and writing the elements in increasing order will ensure that no combinations are overlooked. So you have these combinations starting with 1. These combinations start with 1, 2. It starts with 1, 3, or 1. Additional combinations that start with 2, 2, and so on and so forth. So there are 23 combinations with repetition allowed. The number of R combinations with repetition allowed that can be selected from a set of n elements is R plus n minus 1, choose R. This equals the number of ways R objects can be selected from n categories of objects with repetition allowed. A person given a party wants to set out 15 assorted cans of soft drinks for his guests. He shops at a store that sells 5 different types of soft drinks. How many different selections of 15 soft drinks can he make? If root beer is one of the types of soft drinks, how many different selections include at least 6 cans of root beer? And see, if the store has only 5 cans of root beer, but at least 15 cans of each other type of soft drink, how many different selections can there be? Well, think of the 5 different types of soft drinks as the n categories, and the 15 cans of soft drinks to be chosen as the R objects. Each selection of cans of soft drinks is represented by a string of 5 minus 1 or 4 vertical bars to separate the categories of soft drinks, and 15 crosses to represent the cans selected. For instance, this string here represents a selection of 3 cans of soft drinks of type 1, 7 of type 2, none of type 3, 3 of type 4, and 2 of type 5. The total number of selections of 15 cans of soft drinks of the 5 types is the number of strings of 19 symbols, and it comes to 19 factorial divided by 15 factorial times 19 minus 15 factorial. Do some calculations and cancellations and multiplications, and you get 3,876. If at least 6 cans of root beer are to be included in the selection, you can imagine choosing 6 such cans first and then choosing the 9 additional cans. The 9 additional cans can be represented as a string of 9 X's and 4 bars, vertical bars. For example, if root beer is type 1, then the string given here represents a selection of 3 cans of root beer, in addition to the 6 already chosen, none of type 2, 2 of type 3, and 4 of type 4, and none of type 5. So, the number of selections of 15 cans of soft drinks of the 5 types, including at least 6 cans of root beer, is the number of strings of 13 symbols, which is 4, 5 minus 1, the 5 types minus 1, and 9 of the representing the remaining cans of soda beyond the 6 original, the first 6 root beer. Multiply that out and do some cancellations and stuff like that, and you get 715 combinations. If the store has only 5 cans of root beer, then the number of different selections of 15 cans of soft drinks of the 5 types is the same as the number of different selections that contain 5 or fewer cans of root beer. Let T be the set of all possible selections, assuming that there are at least 15 cans of each type. Let R sub less than or equal to 5 be the set of selections from T that contain 5 or fewer cans of root beer. Let R greater than or equal to 6 be the set of selections from T that contain 6 or more cans of root beer. So T would equal the union of those two sets, and R sub less than or equal to 5 intersected with R greater than or equal to 6 equals the empty set. They are disjoint sets. No intersection. By part A, n of T is 3,876. By part B, n is n of R sub greater than or equal to 6 equals 715. So by the difference rule, n of R sub less than or equal to 5 equals the difference between those two numbers, which is 3,161. So if there's only 5 or fewer cans of root beer, then the number of different selections of soft drinks is 3,161. Counting triples. If n is a positive integer, how many triples of integers from 1 through n can be formed in which the elements of the triple are written in increasing order but are not necessarily distinct? In other words, how many triples of integers I, j, and k are there with I and j and k being less than or equal to n but greater than or equal to 1? Any triples of integers can be represented as a string of n minus 1 vertical bars and 3 crosses, with the positions of the crosses indicating which of the 3 integers from 1 to n are included in the triple. This is illustrated for n equals 5 here. Just giving an example of what they're meaning by this. Thus, the number of such triples is the same as the number of strings of n minus 1 vertical bars and 3 x's, which is n plus 2 choose 3, or n factorial, or n plus 2 factorial over 3 factorial plus times n plus 2 minus 3 factorial. When you multiply things out, do a bit of cancellation, you get n times n plus 1 times n plus 2 all over 6. How many solutions are there to the equation x1 plus x2 plus x3 plus x4 equals 10? if these four numbers are all non-negative integers. Think of the number 10 as divided into 10 individual units, and the variables x1, 2, 3, and 4 as four categories in which the units are placed. Number of units in each category, x sub I, indicates the value of x sub I in the solution to the equation. Each solution can then be represented by a string of 3 vertical bars to separate the 4 categories, and 10 crosses to represent the 10 individual units. So you get the examples here from the possibilities. Therefore, there are many solutions to the equation, as there are strings of 10 crosses and 3 vertical bars, namely 13 choose 10. 10 vertical crosses, 3 vertical bars, and choose 10 combinations. Choose 10. Expand it out, do some cancellation, gives you 286 possible solutions for that equation. Remark: deciding which formula to use. This table here shows which formula to use in which situation. I highly recommend writing this down for use on the final exam. If repetition is allowed and order matters, there are n to the k possible combinations. If repetition is allowed and order does not matter, it's k plus n plus or minus 1, choose k. If repetition is not allowed but order matters, then it's the number of permutations of n and k. And if order does not matter, and repetition is not allowed, it's n choose k. So I'd take a picture of that table and have that handy for the final exam. Or print out the slide when you get back to wherever you're going for the Thanksgiving break. Three brief slide decks for the day. But the final exam is going to be Tuesday at, when is it going to be? Tuesday at noon to 2, I think, is the time of the final. Don't quote me on that. I don't remember off the top of my head, but it is on Tuesday, Tuesday afternoon. So be ready for that. Have all your notes organized and printed out. The final is open note. It is comprehensive. It's going to have 3 questions from the first 5 chapters, and then 5 questions from chapter 9, because we haven't tested on chapter 9 yet. We don't have time for that. So, yeah, the final. 5 questions from chapters, or 3 questions from chapters 1, 2, 3, 4, and 5, and 5 questions from chapter 9. Three from each chapter. So 20 questions total.
3 from 1, 2, 3, 4, 5.
and 5 from Chapter 9. Chapters 6 and 7 are extra credit and are not going to be included on the final exam. I do recommend you doing the extra credit. Those 2 chapters, 6 and 7, are interesting chapters. They're not long. There's only 4 sections each. And you can substitute your homework grades from those chapters for lower quiz, to bring your quiz or test grades up if they are better than your quiz or test grades. For 6 and 7, yes. If you do chapter 6 or 7, but not both, the average from the homework, if it's higher, will replace your lowest quiz grade. If you do both 6 and 7, the higher of the 2 averages will replace your lowest test grade if it is higher than your lowest test grade. So also, if you've missed any quizzes or tests so far this semester, you must have them done by this Friday. See me in my office. We'll get you caught up. I've been busy this week so far, doing makeups and all that sort of stuff. People missed because they were sick or at conferences or whatever. You have until Friday to make them up. If you don't make them up, they will be at 0. But you do have that extra credit option. So if you want to skip doing the makeup and just do the extra credit, that would be fine too. The extra credit cannot hurt your grade. It can only improve your grade. So no worries about that. Though the extra credit is, I believe it's open until the 3rd of December. So that's Wednesday of finals week. Let's see here. Any other announcements? I think that's about it. Let me see here. See here. Calendar. Discrete structures is, I'm sorry, it's 1 to 3. The final is 1 to 3 on Tuesday, December 2nd. So 1 to 3. It's a 2-hour final, or 1 to 2:50. And 20 questions, as I outlined a few minutes ago. Yeah, should be good to go. And final grades are posted on Pause and Canvas by Friday, or by the Monday the 8th at 5 p.m. So that's when I have to have all the grades in. So you will know for your winter break what your grade is. Anyway, have a good day, all. See you on Thursday. We'll finish up Chapter 9 and get ready for the final.